reliability is essentially error-free operations. Now, error-free in every way you can think of. From the client being greeted, to the correct file being extracted, to waiting times, to the correct intervention being applied, all across the board, we want to be error-free. But you know that as humans, it's impossible to be error-free because we're human and humans will err. So what we have chosen as the standard for high reliability is 10 to the minus 6. What is 10 to the minus 6? It is kind of one error per every million events. So for every million people that we greet, we are allowed to skip one. Okay? That is the definition of high reliability. So for every service that we execute, we are allowed to fail with one. For every million anything we do, we are allowed to fail one. That's the definition of high reliability. Now, of course, that's difficult to do, but there are industries and sectors that actually do it. So there's no excuse for social services not to achieve that. Now, 10 to the minus 6 is also equivalent to about 6 standard deviations from the mean. Now, the mean is the average. Okay, we calculate the average. So we collect data points, we calculate the average, and we also calculate the standard deviation. The standard deviation is a calculation. Okay?
One second, Prof. He's saying we can't see you. Just ask them if they all can't see you.
Can you guys see and hear?
We can hear, we can't see you, Prof. We see you, but we can't see you.
Okay, let's just correct that.
See you?
You can see?
Yes.
Okay, we're back. Okay, so let me just repeat. So where we want to get from a high reliability point is 10 to the minus 6, meaning one defect in a million events. And we said 10 to the minus 6 is approximately 6 standard deviations. Okay, from the mean. So we generally do something in 10 minutes. We're allowed to be within 6 standard deviations of that to qualify as high reliability. Okay, that's what it means. Now we have to calculate the standard deviation. That's a mathematical calculation. That's the link I gave you. So we put the data points in, or the scores, or the times, or whatever. We calculate this, and then we graph it out. That's what standard deviation means. It's just a calculation. And generally, whenever you see a mean or average reported, generally, you'll always see it reported as, say, 2.3 plus minus 1. Because you always report a mean or an average with its standard deviation. Okay, so if you read anything, they'll say an average of 2.3 plus minus 1, which is the standard deviation. Now, the lower the standard deviation, the more compact the numbers are. That means that they are closer to the mean. The bigger the standard deviation, it means the variation is high. Okay, so if you have a short standard deviation, a small standard deviation, so let's assume 2.3 plus 0.001. It means the numbers are pretty close. They're close to the mean. If you have 2.3 plus minus 1.2, it means that the numbers are scattered around the mean. That's what it means. The variation is high. So those 10 numbers that we had, they are all scattered quite widely. That's what a larger standard deviation means. Is that clear? So standard deviation, just by looking at a standard deviation, you can get a sense of the variation in the numbers. In those 10 numbers that we have, if the standard deviation is high, it means those numbers are 2, 10, 15, 1, 3. If the standard deviation is low, it's going to be 10, 10, 10, 10.5, 10.6, 9.9, etc. That's what it means. Now, some organizations will operate off a low standard deviation. They will not be tolerant of 6 standard deviations. They'll say we want to operate at a very narrow standard deviation, which means that you know, whatever you do, your error rate is going to be very narrow. The range is going to be very narrow. Okay? So I'm not sure whether I have clarified or confused it anymore, but if I confused you, I can go over it again. Was that clear in terms of what a standard deviation is? Now
Please, just repeat slightly. I think I missed something.
Okay, so let me go back then. And let's just take, okay, so let's just take, we'll go back to the waiting time because it's the easiest thing. Okay, so let's just go back to that example again. Is that we have measured waiting times to get your file. Okay, we're a small office, so we only see 10 clients a day. So we take all 10. Their waiting time is 10, 9, 8, 7, 4, 11, 12, 5, 6, and 6. 1, 2, 3, 4, 5, 6, 7, 8, 9. So there are 10 clients. These are their waiting times. Okay? We need to calculate 2 things. The mean, which is the average waiting time. Okay? The mean. And then we need to calculate the standard deviation. What is the variation from the mean? That's the standard deviation. Okay? Now this, remember, is a mathematical calculation. We go to that link, we put in these 10 numbers, it's going to give us a mean and give us a standard deviation. Now remember, these numbers are useful. Let's just assume the mean is 8.5 and the standard deviation is 1.1. Remember I said to you yesterday, we cannot manage a mean. You can't manage an average. But you can manage these numbers. And that's the reason we have to develop control charts. The control chart is actually taking these data points and putting them down. 10. So we put all those numbers down. Now we can manage. We can join them. Okay? I can manage this. I can't manage that. Okay? But I'm using this mean and I'm using the standard deviations of 1.1 to determine what we call upper and lower control limits. Okay? This is the lower control limit. This is the upper control limit. What is the lower control limit? It is the mean. What is the lower control limit? That's the mean. That's 1 standard deviations, that's 2 standard deviations, that's 3 standard deviations. The lower control limit is the mean minus 3 standard deviations. The upper control limit is the mean plus 3 standard deviations. Okay, so that's all this is. I'm taking these 10 numbers, I'm calculating the mean and standard deviation. The only reason I'm calculating this is so I can draw this chart. But the chart has these numbers in it, relative to the mean and relative to the standard deviation. So we know patient 1 took 10 minutes. That was above the mean, but it's within the upper control limit, so it's fine. We know that one patient took 5 minutes, was very short. We know it's below the mean, but it's still above the lower control limit. Because remember, if something is below, even if a patient took 2 minutes, a client took two minutes, we need to understand why is it that this person only waited 2 minutes. Could there be something that was missed? And was there something not done that enabled this client to only wait 2 minutes? On the other hand, if they waited 15 minutes, we also need to investigate. So the point of having this is that we investigate stuff that's above the upper control limit and above the lower control limit. Okay? Everything in between is fine. Now, you can still see in between we have this variation. Then it goes like that. We call that normal cause variation. The variation within the upper control limit and lower control limit is acceptable. It's normal. Because you can never do the same thing taking the same time every single time. So any number above the upper control limit or below is called special cause variation. We have to investigate it. Now this takes us back to the fact that I'm not using an average. I can't manage an average. I can only manage these numbers, and the numbers I want to manage are the ones that are not within 6 standard deviations. Okay, do you get it, or is there anything specific that I need to re-emphasize? Okay, can I clarify anything else? It's important. I know if it's the first time you've seen stuff like this, it can get confusing. Do I need to... Who's still not comfortable with this? Who's still not comfortable and confident with it? Sorry?
Can you repeat the normal and special cause?
What do I need to repeat? Which part?
Normal and special cause.
Okay. So yeah, right, that's a good question. And I can understand why you get confused because I'm using the words variation and deviation, okay? Now deviation I'm not using alone. The only time I say standard deviation. Standard deviation is a mathematical calculation. Variation, this is variation. Okay, this is variation. Now, we have plotted the control chart. We have the mean in the middle, and then 3 standard deviations below gives us what's called the lower control limit. 3 standard deviations above the mean gives us upper control limit. Remember, between the upper control limit and lower control limit, that's 6 standard deviations from the mean. 3 above, 3 below. That's where we want to be, because 6 standard deviations equals to 10 to the minus 6, approximately. Okay? So the variation, the numbers between these two upper control limit and lower, the variation between them is called normal cause variation. So it means it's acceptable. It's different, but it's acceptable. Once you go above the upper control limit and below the lower control limit, we call that special cause variation. Now, the significance of special cause variation is that we have to investigate it. Now, this is the purpose of collecting the data and doing this graph. Because now we're not investigating everything. We're trying to investigate what happens up here. Because this is above the upper control limit. That's what we want to investigate. And this may well be the January average wait time. January, say January 2021, we had this. Now we need to investigate, well, what happened in January that resulted in the wait times there being high. And I'll give you some ways to actually do that now, but this is what you would do. This is the purpose of doing this. But if we worked off the average, we would not have found this an issue. This is why I say, from a management point of view, and specifically from a high reliability point of view, don't give me an average, because the average does not help me. I want to know the actual data points and how they relate to the mean and standard deviation. That's what I want to know. Okay? Is that clear? So that's the difference. Special cause variation means you have to investigate. Normal cause variation is acceptable because normal cause variation by definition is between the upper and lower control limits. Any other questions? Do you want me to go over that again? Are you okay?
We are above, we can go on. So,
Yeah.
it means that it's special, if there's a special cause variation, it means it's where the organization doesn't want to be as an HRO.
Yes. It also means you got to work to it. It means you got to investigate why it's happening.
Okay.
That's what it means. So you can only pick that up with this. You can't pick it up if you got the average. So at the end of the year, if you've got average wait times, Jan, Feb, March, April, May, right till the end, at the end you say, well, Prof, the average wait time is 8.5, and then generally the managers and everybody's happy. Oh, great. Because you misinterpreted the whole thing. And I get a lot of that. It is, you can't manage an average. By mapping the way we did it, you suddenly can see where the variation is, what needs to be investigated, and what's tolerable. Now remember, what I said to you yesterday was, even if you're in between the upper and lower control limits, let me erase this and start again. Okay, this is messy. Because I think these are important concepts for you to grasp. Really important. I mean, this is kind of why we call the session quantitative methodology, because you manage by the numbers. You can't manage what you can't measure, okay? So, this is it. Remember, we put the mean. That's the mean. The mean is the average. We calculate the mean. Vic, maybe if you just want to focus this camera a bit more close on this. So, okay, so we got the mean. And then we also have, we're plotting, what do we plot? So we got the mean, what else do we plot? We plot 3 standard deviations below. Okay, so that's 1 standard deviation, that's 2 standard deviations, and that's 3 standard deviations. You know this by now, okay? 1, 2, 3. The same above. 1 standard deviation, 2 standard deviations, and 3 standard deviations. Okay? That's what your control chart will look like. We calculated the mean. We know what the standard deviation. We calculated the standard deviation. we now draw the line. The mean minus 1 standard deviation, we draw a line. Minus 2, we draw a line. Minus 3. The mean plus 1, we draw a line. Plus 2, we draw a line. Plus 3, we draw a line. We now have the upper control limit and we have the lower control limit. Okay? So we now have, just by calculating, so we got the data set. We've taken the data set, we've calculated the mean and the standard deviation. We have now plotted the graph. We have developed this. So we know what the mean is. We know what's 3 standard deviations above. We know what's 3 standard deviations below. Because we've calculated it. We've drawn. That's given us the parameters for normal cause variation. Any number that we put in here is normal cause variation. Any number that falls outside is special cause. So we go back to our set of data that we collected and we take the numbers out and let's assume it was average wait time for January to December. Okay, so we'll have Jan, Feb, March, April, May, June, July, August, September, October. Okay, those are 12 data points in this case. And now we've got the number, so we put those numbers in. Okay. Okay, so it'll go like that. Okay. So if you can see, so how did we get here? We had 12 readings. Average wait times for every month. We had 12 readings. We took those 12 numbers, we put them into that software, and we calculated the mean and standard deviation. We got the mean, and then we draw these lines, 3 standard deviations below, 3 standard deviations above. The top line is called the upper control limit. The bottom line is called the lower control limit. Then we take those 12 numbers and we plot them in. We are looking for points above the upper control limit and below here. So straight away we know that there was an issue in November and there was an issue in December. Although the average would have been fine. But that's not how high reliability organizations operate. Okay? We need to investigate why the wait time in November was high and why the wait time in December was low. We need to investigate that. Okay? Now you can see the wait time in between was like this. That's called normal cause variation. It's different, but it's acceptable. The only reason that it's acceptable is because it's between the upper control limit and lower control limit. This is special cause variation because it's above and below. Okay? The other thing is you can also see here, we've got 1, 2, 3, 4. We've got 4 successive increases in wait time. Jan, Feb, March, April. High reliability organizations watch that. Okay? They say, well, is this a trend? And you can see up here. Okay? 1, 2, 3, 4. We have 5 successive increases in wait time. We can make a reasonable inference that the system, although is stable, it's the first sign that something is going wrong because you're getting these successive increases. You can't pick this up on an average. Okay, because this is now, you won't investigate if there's 4 or 5 successive increases. If you're getting to 7 or 8 increases or decreases, that's also an investigation. Okay? Now you can only do this with real-time data. So not only do you investigate special cause variation above upper control and below lower control. You also investigate when you have a situation of 7 to 8 successive increases or 7 to 8 successive decreases. Okay? Any questions about that? I'm okay to stand here and go over this the whole day if I have to, but I think you need to get it. But repetition, you'll get it, because I'm kind of saying the same thing over and over. Is anybody still a bit uncomfortable, still a bit uncertain about this?
Yeah, yes, Prof. Can you repeat yourself?
Can I repeat myself? Okay. Okay, let's do an exercise. Okay, let's do an exercise. Okay? Let's do an exercise together. Do you have some paper and pencil there?
Yes, yes.
Okay, good. Let's do the exercise. I think it's going to be the best.
Yeah, that's an example.
Let's take an example.
And please
Yeah.
make sure for the board to be clear, please.
Okay. Is this clear now?
Thank you. Yes, we can see now.
Okay. So once again, I'm going to take the waiting time because it's simple. We're going to come back to everything else, but let's take the waiting times. Okay. So up at the corner here, I'm going to put, we measured. So from the time the client walks into the office till the time they get the file in the hand, that's the wait time. So we are there with a stopwatch. Okay? We're standing with a stopwatch. Client walks in, click. Client receives the file, click. That's giving us the time in minutes, the wait time to collect the file. We're going to take 10 people or 12 people, whatever it is, because remember I gave you the sample size. Now let's repeat that just to make sure about sample size. Okay, I'm going to write that at the bottom. Vic, you might want to just focus this camera here. Remember, I told you, how do we determine how many we collect? That's easy. If you have a total of less than 30, you take all. If it's between 30 and 100, you take 30. If it's 101 to 500, you take 50. If it's more than 500, you take 70. Okay? You got this? Did you get this?
Please repeat it, Prof. So sorry. Please repeat it again.
Okay, we are now calculating sample size. That's going to determine how many clients do we actually measure. Okay, that's what we do. How many clients do we measure? And what I'm saying is, you don't have to measure the time for every single person that comes in. The number that you choose depends on the total number that you see per day or per month. You want a random sample. So let's assume that we want to do it over one day. If you see less than 30 clients in the day, you choose all 30 to measure the time. If you see between 30 and 100 clients a day, you can't take 100. You take a random sample of 30. Okay? If you see between 101 and 500 clients a day, you take a random sample of 50. If you see more than 500 a day, you take a random sample of 70. So, the maximum number of data points that you actually will ever need is 70. Irrespective of whether you see 500 clients or 5,000, you will only need 70. Because statistically, if you analyze a random sample of 70 and the 5,000, the numbers are the same. It will come to the same. This is the whole purpose of sampling, is you don't do the whole population, you just choose a random sample. Okay, so that's the first thing you have to understand. Now, what I'm going to do is, let's assume ours is a small office. We don't see too many clients every day. Let's assume we see 15 clients a day. Now, 15 clients, we know based on this, 15 clients is actually, sorry, this is the wrong, 15 clients is less than 30. How many do we sample now? If it's less than 30, how many do we have to do?
All of them.
We have to do all of them. Good. So now we're measuring them. We need 15 data points here. Okay, so there's the 3 minutes, 5 minutes, 8 minutes, 7 minutes, 10 minutes, 12 minutes, 4 minutes, 5 minutes, 7 minutes, 6 minutes. 2, 4, 6, 8. 2, 4, 6, 8, 10, 12. And then that's 10 minutes, 9 minutes. Okay, 3, 6, 9, 10. That's 15. So there's our 15 clients. Write that down.
Please,
Sorry?
the board.
What about the board? You want to see the board?
Yes.
Okay,
Yes.
just focus here. So this is the time. Can you see this? Can you see these times?
We can see. Yes.
Okay. So let's rewind. Because we saw 15 clients, 15 is less than 30. We took all, we measured the 15. This is their waiting times. So we got 15 data points. 15 patients, this is their wait time. What do we have to do next? What do we have to do next?
We need to calculate standard deviation.
Good. We need to calculate the mean and the standard deviation. How do we do that?
By feeding the waiting time.
You feed, you go, Vic, let's just do that.
8.2.
What, okay, did you calculate it already? So we go to the website, we pull it up, how to calculate. Okay, share the screen, Vic.
Can you have the number on the board?
Sorry?
Can we have all the numbers on the board because it's quite crucial.
3, 5, 8, 7, 10, 12, 4, 5, 6, 7, 11, 13, 10, 9, 8.
I got 3
What did you get? Okay, you scroll that up. Okay, can you see the Vic screen now? Okay, so we're doing the exercise with you. Okay, we're putting in the numbers. These are the numbers that are on the board. Okay, and now,
8.2.
okay, go ahead now, scroll down. What is the we're choosing what? What are we choosing?
The sample.
Eyeball.
Population.
We're choosing population, good. Why? Because we chose all below 30, everything. Okay, good. Calculate, Vic. Okay, so here we go. We have a mean of 7.87 and we have a standard deviation of 2.87. Okay? So it's a reasonable standard deviation, means that, you can argue it's a bit high, means that there's a lot of variation, but that's what it is. Okay, we can exit. So you know now, up to this point, how to get to mean and standard deviation.
Yes, Prof.
Okay, good. What do we do now? What do we do now? What do we do now?
Do we plot?
We plot. Good, good. Okay, so we plot. What is this line? What is the main line here?
The mean.
The mean. The mean is what? 7.8.
8.
7.8. 7.8.
Our upper control limit is the mean plus what?
Plus 1.
Huh?
Plus 3.
Plus 3 what?
3 standard deviation.
3 standard deviations. Good. What's 3 standard deviations? 3 times 2.87 is what? Calculate. 3 times 2.87. What's 3 times 2.87?
8.61.
8 point?
61.
Okay. So upper control limit will be 7.8 plus 8.61. What is that? What does that give you? 7.8 plus 8.61 is what?
16.41.
16.41. That's the upper control limit. Because the upper control limit is the mean plus 3 standard deviations. What is the lower control limit? The mean minus 3 standard deviations. So it's 7.8 minus 7.8 minus 8.61 is what? Sorry?
Population.
7.8 minus 8.61. You're going to get a negative number.
Negative 0.81.
0.81. That's the upper control limit. That's the lower control limit. Now you can't get a negative wait time. Okay, so you can actually zero it, but we leave it here. You got a lower control limit. Okay, so up to now, are you clear how did we get here?
Yes.
You clear? Good. What do we do next? What do we do next?
We populate those.
That's it. We populate. We take these 12 numbers and we start putting them, okay? 3, 5, 8, 7, 10, 12, 4, 5, 6, 7, 11, 13, 10, 9, and 8. And then we join them. Okay? Now you know how we got there. Do you know how we arrived here now?
Yes. Yes.
Okay, so it's pretty simple. Now we're looking. What are we looking for?
We are looking at the frequency or the.
Special cause variation.
Yes.
Excellent. We're looking for special cause variation. Is there anything above the upper control limit, anything below? In this case, is there anything above or below?
No.
No. Okay, so at the moment, first glance, we are happy. It means this process is stable. That's what it means. No immediate things to investigate. Except when you look closer, what else are you looking for? You're looking, well, okay, everything is fine, but is there anything in this data that I need to be observant about? And what you see here is what? 1, 2, 3, 4, 5, 6. 6 successive increases. Can you see that?
Yes.
It means, well, we've got to look because there's a hint, there's a suggestion that something is going wrong. That is what is called sensitivity to operations. You see? It is, we can only be sensitive to the operations if what? if we have collected the data, if we have mapped it, and if we can make sense of it. Because although this is within the normal upper and control, there's a suggestion, there's a hint that something is going wrong. And we need to pay attention to it. Okay? That's all kind of, this is what data-driven management is all about. You are not going to get to this by just saying the average wait time was 7.8. That's bad management. You can't manage an average. Okay? So, very important lesson. You cannot manage an average. Very often, means or averages are all acceptable. But you can't manage that. Sensitivity to operations means you need this level of data to be able to drill down. Okay, so this is kind of how we got here from yesterday and today. Any questions that we still need to clarify? Because I'm not going to move on if you don't get this. This is the heart and soul of data-driven management.
Prof, for the last time,
Yeah.
please repeat the calculation
Okay.
for the upper cause limit and the lower
Cause limit. Okay, so it's upper control limit, lower control limit. Sorry?
Yes, Prof, for control limits, I got it wrong.
It's control limits. Now the upper control limit is the mean plus 3 standard deviations. One standard deviation is 2.87. So we multiply that by 3. That gives us the upper control limit. The lower control limit is the mean minus 3 standard deviations. So it's 7.8 minus 8.61, which is 3 standard deviations, and we get. Okay? Now, between the upper control limit and the lower control limit is 6 standard deviations, 3 above and 3 below. Okay? Remember, 6 standard deviations is approximately 10 to the minus 6 errors. So we're all kind of coming back to the same thing, is high reliability operates at 10 to the minus 6, almost defect free. Okay, so you understand that upper control limit, lower control limit. Upper control limit is mean plus 3 standard deviations. So it's mean plus 3 times standard deviation. Lower control limit, mean minus 3 times standard deviation. Okay, and you make another note. Investigate 1, special cause variation. Special cause variation equals above control limit or below control limit. Investigate 2, upward trends or lower trends. An upward trend meaning about 7 consecutive upwards, lower trend meaning about 7 consecutive drops. Okay, anything else? Now please, as I said, do not be afraid to ask if you don't understand. Okay? Because if you don't understand, it means somebody else doesn't understand too, but they're just afraid to ask. And this is actually, surprisingly, it becomes fun when you start getting used to it and you make it part of a habit of leading. This is what management and leadership is all about, by numbers. Not intuitive management, where you just assume and guess and do stuff like this. Okay? And this is what we're infamous for in the public sector. We lead and manage by intuition, not by data.
Prof,
Yeah.
can you please repeat for the last time the calculation of the mean when using the website? I didn't get that clearly.
Okay, so we're going to pull this up. So you got the numbers, okay? You go to the website. You go to the scroll up. You go to the website. You want to clear that out? Okay, you go to you can use whatever website you're comfortable with, please. Okay, this is just the one we picked up, and Vic, we just found it here. There's several other ones you can use. So you go to the website that's there. It says type in the scores. So what Vic is doing now, he's typing in these numbers that we have. This is the wait times. That's what he's doing. He's typing in the numbers.
Yes.
Okay? Exactly as they are. And then he's choosing the population. You know why he's choosing the population?
Yes, because we're not using the sampling, we're using the whole population.
That's it. And now you click calculate, and there it's giving you their standard deviation calculation. So the n, the number 15, is the actual data points, because we've got 15 numbers here. The mean is the average is 7.87, and then the standard deviation right at the bottom there, you can see it's got that sigma sign, is 2.87. That's it, highlighted.
2.87.
Yes.
Where's that? Or standard at the end.
Yeah.
Okay.
Right. That's how you calculate it. Now you've got to practice. Just put in some random numbers, put in whatever, doesn't matter. You know, age group of your family or whatever you want to put in, do that. And practice it. Yeah, just keep this website on the tab usually. You can just pull it up quickly and get you. So it should go very quickly. It's, and now all you have to do is once you get the standard deviation, you multiply it by 3. Mm-hmm. Okay? And when you multiply it by 3 and you add it to the mean, you get the upper control limit. When you subtract it from the mean, you get the lower control limit.
Okay.
Okay? Because the upper control limit is the mean plus 3 times the standard deviation. The lower control limit is the mean minus 3 times the lower control limit. Sorry, minus 3 times the standard deviation.
Nice.
Okay.
Okay. Thank you very much.
Anybody else?
And where do we get the link?
We sent it to you on the chat, but you can just Google how to calculate standard deviation. It'll give you several links that you can use. Essentially, all they'll ask you to do is put in the scores, put in the numbers, and hit calculate somewhere. It's back. Vic has just posted it on the chat again today. He did that yesterday as well. You can use that as I said. Yeah. Anything else before we move on? But if you feel very comfortable up to this point, you should feel good about yourself, because I think it's a major achievement moving towards management by numbers. You should, feel good. It's something, and then it's something you can already start using tomorrow when you're actually back at the office. Okay? Can I move on, or is there anybody still not comfortable, not feeling confident, still have some uncertainty about anything? Can we move on? Are you now comfortable?
We are fine, Prof.
It's coming together. It's coming together.
Yes.
Okay, good. Okay, I'm going to erase this. Practice makes perfect. When I first started this, I was lost myself. Okay, so if that makes you feel better, then I had the same issue of grasping all of this thing, but it comes with practice and it comes with time. Okay, this is not something that physicians do. This is not something that social workers do. But when we start moving into management, we have to be able to do this, to become good managers and good leaders. Okay, let's move on. There were some good questions asked. Well, okay, why did I use just time? What else do we measure? And good question, okay? The only reason I used time was because it's just the easiest and something that everybody uses, okay? What I want you to do now is kind of give you a reliability management process, okay? Let's just call it a reliability management process. Okay. How do we actually, so what is the framework to actually manage reliability within your organization? Now you've got components of it already, but we have a kind of well-defined approach to actually do this in a very systematic way. Okay? So the first thing is remember, everything in management, in reliability management, begins with what? Begins with what?
Process map.
Absolutely brilliant. Everything begins with process mapping. The heart of data-driven management is about process mapping. And remember, when you map a process, your frame of reference is the client. Okay? Your frame of reference is the client. So the process map is in effect the path that the patient, the client actually follows. Okay? So life in the space of reliability management begins with the process map. I mean, in other words, walk the path of the client. Okay? That's what it's. And then we've got a fixed reliability management process. Now, that starts, the first step of that is measurement. In other words, we have to measure. And what we measure depends on our organizational goals. Okay, so we're going to come back to that. But measure. The first thing we measure. Now, you already got a taste of measurement because we measured waiting times. Now, if waiting time is a key organizational goal, then you've kind of been through a process already. Okay? Remember, we measured 15, we took all, we got the mean, we got the standard deviation, we plotted it. That's measurement. Okay? So the first step is measure, and what you measure depends on your organizational goals. Now, DSD may have certain specific goals that they want to accomplish, and those are the things that you will measure. Okay? Then we have to assess. It's assessment. Assessment is the next step. Now, when we measured waiting times, we put the mean, we put the standard deviations, upper control limits, and what I said to you, if it's all kind of in between, you have a stable process. If it's above the upper control limit, below, or there's any trends, it means you have special cause, you have to investigate that. Okay? Assessment entails observing that. You're assessing to see what is wrong. But you're also assessing to see if there's gaps in performance. Now, you may have a stable process in your office, meaning that the waiting times are all within the upper and lower control limit. It means it's stable and reliable. But when you compare your data, your control chart, to Office B and Office C, and you find, well, their mean is not 7.8, but it's 4.3, and they have a lower standard deviation than you, you know that there's a gap between you and them. So the assessment is what you're asking yourself, is there a gap in performance? Now I can tell you there's always a gap in performance because where you want to be is at 0 defect. Because 10 to the minus 6 by definition is almost 0 defect. So you think about this, for every 1,000,000 clients, you can kind of get it wrong. The maximum you can get it wrong is about 3.4 times. But generally it's between 1 and, so approximately 1 out of 1,000,000. To make it simple, okay? That's where you want to be. In effect, for practical purposes, it means 0 defect. That's what it means. So there's always a gap. So even wait time should theoretically be 0. Theoretically, because you don't want anybody to wait, isn't it? If you actually have an optimal system, the client should not have to wait at all. Okay? I mean, it's like, I'm sure every one of you has flown. Did you ever land and have an experience where the aircraft taxied and had to wait 10 minutes before it went to the gate? Or what happens? It lands and it taxis and goes straight to the gate and you get off. There's no wait time for the gate. That's 0 wait time. Why? Because they're high reliability. They're managed by data. The plane never lands if the gate is not available. So theoretically, 0 wait time is possible, where the client walks straight in, collects their file and goes away. That's where you should get to. That's what high reliability is. That's what top performance is. So what I'm saying is, in the assessment, there should never be comfort. So even if you're stable, it doesn't mean you're fine. Because I made the point. Reliability does not mean it's the best. It just means you're consistent and you're accurate. You know, so if I have to use another example, if you play darts, if you didn't play darts, you may know what darts is, okay? So if I'm playing a game of darts, I'm actually aiming for the bullseye. That's what I'm aiming for, okay? If I get the bullseye consistently, means I'm reliable and I'm getting what I want to get. But I could consistently hit 20. That means I'm reliable. I'm reliably hitting the same thing, but it's the wrong thing. So you have to understand conceptually that being reliable is not the end game. It's reliability plus perfection. And that is what assessment is all about. Can we become perfect? Can we get the bullseye? It's great that you're hitting 20 all the time, but where we really want to be is hitting the bullseye all the time. Okay? And so when we measure and assess, this assessment is actually, well, okay, how do we get from hitting the 20 to hitting the bullseye? It's, how do we get from a wait time average of 7.8, although it's reliable, to a wait time of 5? That means we have to still change. We can't be happy. So the measurement we drew, all fancy, you got that. But that's not where it stops. That's the first step. We've measured, now we've got to assess. What does it mean? How does this compare to other organizations, other offices, other similar offices, okay? So what we're trying to say, is there a gap in performance? And then, so is there a gap? Okay? And what you want to answer is you're obviously going to find a gap because you're never perfect. Okay, so if it's no, you don't have a problem. But generally you're imperfect because you want to be at 10 to the minus 6. So what is the causation? You want to assess, well, what is wrong? Why are we at 7.8 yet our peers are 5? Okay, so what is is the reason that we're not at the level of our best? What is the reason that we're at 5 and not at 1? So these are the questions you have to try and figure out. Why and how can we actually improve it? Okay? So it's what is the causation of that? The next is what is the solution? What do we do? So why? How do we change? So what's the solution? Okay. It's improvement or implementation. It's monitoring. And then it's assessment again. So this is the reliability management process. Okay, we measure. What we measure depends on organizational goals, and I'm going to come back to measurement. Assessment. Assessment is how far are we from 10 to the minus 6? How different are we to other similar peers? How different are we and what's the gap? Why are they far better than us? If there is a gap, which there will be, what is the causation? What is the reason that the wait times are much longer or not where they should be? Or what's the wait time? What is the reason that it's 7.8 and not 4? Okay. How do we actually address this? Okay. And how do we implement it and then monitor? Now you can see from yesterday's case, it's pretty much the same thing. You know, the airlines spend, the assessment, of course, is something going wrong. And what did you call it? The consequence. Okay, what do you find out is what is the causation? Remember, there's never a single cause. It's always multiple causes, and generally you get a consequence when all of these causes converge. Okay, that's what happens. And then, well, how do we solve this? That's a set of skills and tools that you need to come up with solutions. Now, a lot of that we'll actually be doing in your final module, where we give you skills to be more creative, innovative, entrepreneurial, come up with tools to actually come up with ideas, and then how do we implement, and then how do we monitor. So this is this reliability management process, and what I want you to do is now sketch that out, draw that out, okay? Draw that out. So number one, reliability management begins with the process map. Okay, so that you cannot start this without process mapping. So one of the first things you should do when you get back to work is choose the most commonest service lines or the most commonest things that occur and develop the process maps. Remember, once you start putting data into these process maps, the time it takes, etc., to fulfill each task, total times, it's then called a value stream map. Okay, so we have to do value stream mapping. That's the first thing. The second is you need to understand this management process. Okay, the management process starts step one, measure. We have to measure. We measure based on what the organization wants to achieve. Okay? What's the organization? That's important. Sometimes that's prescribed to you. Sometimes that's done at local level at your office. But we'll talk more about that. You then assess, meaning you're comparing your measurements to maybe historical precedent, your previous term. You're comparing it to others. And you're comparing it to the ultimate goal of high reliability organizations of 10 to the minus 6, which is you want to get to zero defect. Okay? If there's a gap, if you're at zero defect, there's no gap, you're fine. You go back and measure, but you know we operate generally at 10 to the minus 1, generally, you know, in public sectors. Okay? Normal organizations, commercial operate at 10 to the minus 3. If there's a gap, we need to find out what's the causation, and then what's the solutions, and then here, the implementation of these, how do we do this, and then the monitor. Now some of this you may have covered in other programs and stuff. So it's not this is not rocket science. It's almost a kind of generic approach. I'm not sure if your consequence management approach has the same flow, but this is, you can pretty much use this for anything, okay? Measure, assess, determine cause, come up with solutions, implement the solutions, monitor, and then assess again. So this is this kind of iterative process. Any questions about this? That's just the reliability management process. So remember, 1, map, create the process map. 2, you're going to follow this reliability management process. Any questions up to here? We're now going to take this part of measurement and kind of focus more on that. Any questions about how did we get here so far? Anything that I've put up so far? Any questions? It's just a framework, by the way. It's just a framework. And what we're going to do is flesh out everything in these boxes as we move forward.
Prof,
Yeah.
I'm taking it the reason why we do reassessment will be informed by what we get from from the monitoring process. Unless if I didn't hear you well.
Yeah, the reassessment, yeah.
Yeah.
Yeah, so monitoring, if you monitor, you're still assessing in terms of have you made an improvement and why not? If not, what's the causation, and you start again. So this is, reliability is an iterative process. You're constantly, I mean, you may have improved and you got from 10 to the minus 1 to 10 to the minus 2. That's good, but you actually want to get to 10 to the minus 6, so you have to start again.
Okay, thanks.
So it's a continuous process until we get to 0 defect. You guys need a break? What's the time, Vic?
11:45.
11:45. You need a break? A short lunch break and come back? Or should we go on?
Body break, please.
You want a break?
Body? Yes, please.
Okay. So let's just then give you your lunch break now. How long do you want? 45 minutes, come back at 12:30?
It's fine.
Yeah, come back at 12:30, and then when you come back, we're going to flesh out the measurement. So what do we measure? How do we measure it? How do we collect data? All of that. That's kind of the key to everything else. Okay? So we'll spend some time on that. But you've already got some kind of expertise already. Okay, I'll see you at 12:30. Get some lunch, and once again, during your lunch break, if you're trying to rewind stuff and you're having issues, please, as soon as we get back, let's flesh that out first before we move on. Okay? Enjoy your break. See you at 12:30.